Integral defined functions algebraically. Now that we have worked with integral defined functions graphically, let's investigate what happens without an accompanying graph. Let's consider some general information about g of x, which is equal to the integral from a to x of f of t dt. Let's use what we know about the relationship between g of x, g prime of x, and g double prime of x to determine the following information about g of x, which is equal to the integral from a to x of f of t dt. Well, g of x is increasing, where g of x or g prime of x is positive and g prime of x is equal to f, where that's positive or above the x-axis. G of x is decreasing, where its derivative, g prime, or f, is negative or below the x-axis. G of x will have a critical value where its derivative is equal to 0 or does not exist, or where f is equal to 0 or does not exist or is undefined. G of x is concave up when its second derivative, or the first derivative of f, is positive, or the slope of the tangent line is positive, which is also shown where the function f is increasing. G of x is concave down when its second derivative is negative, or the first derivative of f is negative, or the actual function f is decreasing. And g of x has a point of inflection where its second derivative, or the first derivative of f, switches from positive to negative, or where the regular function f switches from increasing to decreasing, or vice versa. Now let's try an example for integral defined functions algebraically. We're going to let h of x be equal to the integral from -1 to x of cosine of t squared with respect to t, or dt. Find h prime of x and h double prime of x. Let's get started. By the fundamental theorem of calculus part 1, h prime of x will be equivalent to the integrand of our definite integral, but in terms of x. So therefore, h prime of x will end up being cosine of x squared. And then to determine what our second derivative, or h double prime of x, is, we can take the derivative of cosine of x squared. And when we do that, we are going to have to use the chain rule here. So h double prime of x is going to equal, well, the derivative of cosine is negative sine, the angle remains the same, x squared, but then we have to multiply by the derivative of our angle by the chain rule, and the derivative of x squared is 2x. And then if we simplify it, it'll end up being negative 2x times the sine of x squared. Let's try another example on integral defined functions algebraically. Let h of x be equal to the integral from -1 to x of cosine of t squared dt. Find h of -1, h prime of -1, and h double prime of -1 if they exist. Let's get started. In order to determine h of -1, we have to actually substitute -1 directly in for x in our definite integral that we have here. And when doing so, we will have the integral from -1 to -1 of cosine of t squared dt. Well, whenever you have an integral from one value to the same value, it's going to end up equaling 0 because whatever you evaluate it at, you would subtract the same number, and we would always get that value of 0. Now let's find h prime of -1. Well, by the fundamental theorem of calculus part 1, h prime of x is going to be equivalent to the integrand of our definite integral. So that's going to make it become h prime of x is equal to cosine of x squared. And now we can evaluate that. If we substitute -1 in for our x value, we're going to have -1 squared, which is +1, and then we're going to take the cosine of +1, and that's going to be our answer. Now let's work on finding the solution for h double prime of -1. Well, we already have h prime of x right here as cosine of x squared, so h double prime of x is going to be the derivative of this one. Well, the derivative of cosine is negative sine, and then we'll have x squared still as our angle, and then because our angle is more than just x, we have to use the chain rule and find the derivative of our angle, which is going to be 2x. And then if we simplify this, we'll have that h double prime of x is equal to -2x times the sine of x squared. And now we can evaluate it at -1. When we substitute -1 in for x here, we're going to have -2 times -1, which is +2, and then we'll have the sine of 1. So this will be our final answer. Now let's try working on another example. We're still going to let h of x be equal to the integral from -1 to x of cosine of t squared dt. But then we're going to answer this question. Is the graph of h increasing, decreasing, or neither at x equals 0? And we're going to justify our answer. Let's get started. So to determine if h is increasing or decreasing at x equals 0, we need to calculate h prime of 0. And if h prime of 0 is greater than 0, then it'll be increasing. If h prime of 0 is less than 0, then it will be decreasing. So let's first start by determining what h prime of x is. And we have found that h prime of x is equal to cosine of x squared. So now let's substitute 0 in to our function. So we would have cosine of 0 squared is still 0, and the cosine of 0 is 1. So therefore, because it's a positive value, it's greater than 0, h is then going to be increasing at this x value of 0. Now let's try this example. We still have h of x being equal to the integral from -1 to x of cosine of t squared dt. But now we're going to answer this question. Is the graph of h concave up, concave down, or neither at x equals 1? Let's get started. To determine if h is concave up or concave down at x equals 1, we need to calculate our second derivative of h and evaluate it at 1. And if this value is greater than 0, then our function h is concave up. And if h double prime evaluated at 1 is less than 0 or negative, then h is concave down. So let's first get started by figuring out what h prime of x is. Well, we know that h of x is equal to this integral of cosine of t squared with respect to t. So if we were to take the derivative, we would end up with the cosine of x squared. And now we can calculate the second derivative. And the second derivative is going to be the derivative of cosine is negative sine, and then we have our x squared, and then we have to use the chain rule and multiply by the derivative of our angle, which is the 2x. And when we simplify it, we'll have negative 2x times the sine of x squared. And now the question is asking us to evaluate it at positive 1. So let's substitute 1 in for our x value. We'll have negative 2 times positive 1, which is negative 2, and then we'll have the sine of 1. Now, the sine of 1, what value is that? Well, that's actually a point, if we think of the unit circle, that is going to be in quadrant 1. If we had this value at pi over 3, which is a little bit more than 1, then 1 is going to be a little less than that. And the sine of 1 radian is going to have a positive output value. So therefore, we're going to have a negative 2 times a positive value, and negative 2 times a positive is going to be a negative value, making h double prime negative and the original function h be concave down.